two spacecraft left Earth in 1977 on a 5-year mission. Nobody expected them to still be alive in the 1990s. Nobody expected them to reach the edge of the solar system. Nobody expected the edge to be 2.4 billion miles in the wrong place, or shaped like a deflated croissant, or burning at 50,000 Kelvin, in a way that nobody knew about until June of 2025. And yet, here we are. 49 years later, those two machines are still moving through interstellar space, dying instrument by instrument, still sending data home on a transmitter weaker than your kitchen light bulb. And every major thing they found at the boundary contradicted the textbooks. Tonight we walk the full timeline from the 1977 launches all the way out to the pale blue dot, the heliopause crossings, the magnetic highway nobody predicted, and then we keep going 300 years to the Oort cloud, 40,000 years to the first star, 5 billion years to the death of the sun, and 1 billion years of the golden record drifting through a galaxy that may no longer have anyone left in it. If you're somewhere comfortable right now, stay there. Subscribe if nights like this are your thing. Settle in somewhere cozy and stay until the end. This one is worth it. Part 1. The boundary moved. The edge of our solar system is in the wrong place, not by a little, not by some rounding error that scientists quietly footnote and move on from, by 2.4 billion miles. That's the distance Voyager 1 travelled past, where every model, every simulation, every textbook said the boundary should be before it finally crossed into interstellar space. And here's the part that should stop you cold. We didn't discover this from a lab. We didn't figure it out from a telescope. We found out because a spacecraft launched in 1977 on a 5-year mission with 68 kilobytes of memory and a transmitter weaker than a refrigerator light bulb survived long enough to drive through the front door of our solar system and tell us it was in completely the wrong place. That's not a footnote. That's a rewrite. For decades, the standard model of the heliosphere, the enormous bubble of solar wind and magnetic influence that surrounds our solar system, described something relatively tidy. A comet-shaped structure, wider at the front where the sun pushes into the galaxy, trailing off into a long tail behind it, spherical enough, symmetrical enough, predictable enough. The outer boundary, called the heliopause, was expected to sit somewhere between 90 and 100 astronomical units from the sun. 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. So 90 to 100 of those. That was the prediction. Consensus science, peer-reviewed, textbook-ready. Voyager 1 crossed the heliopause at 121 astronomical units. Voyager 2 crossed it at 119, and when they crossed it, it wasn't a clean wall. It wasn't a sharp edge. It was a magnetic highway that no one had ever predicted, surrounded by plasma behaving in ways no model had accounted for, with a 50,000 Kelvin ring of energetic plasma discovered in archival data as recently as June 2025, a feature so strange that scientists are still working out what to call it. The boundary wasn't just in the wrong place. It was the wrong shape, the wrong temperature, and built from the wrong physics. So let's back up. Let's actually understand what the heliosphere is, because this is where everything begins. The sun is constantly exhaling. That's not a metaphor, it's close to literal. From its outer atmosphere, it continuously ejects a stream of charged particles, electrons, protons, helium nuclei, all moving outward at somewhere between 300 and 800 kilometers per second. This is the solar wind. It flows in every direction, constantly, in a sphere radiating outward from the sun, and as it moves, it pushes, it creates pressure, it inflates a bubble in the surrounding interstellar medium, the thin gas and dust that fills the space between stars. That bubble is the heliosphere. Think of it as a force field, if you want a shorthand. Though it's less like a solid shell, and more like a region of pressure and magnetic influence. Inside the heliosphere, the sun's magnetic field dominates. Outside it, the galaxy takes over. That boundary where solar influence ends and galactic influence begins, that's the heliopause. And for the longest time, we thought we understood it. We thought it was roughly spherical. We thought it sat at a predictable distance. We thought crossing it would be like crossing a border, a clear line, a sharp change, a moment of transition you could point to. Voyager showed us something else entirely. It showed us a boundary that breathes, that shifts, that channels particles in ways that shouldn't be possible under classical models, and that sits dramatically farther from the sun than anyone calculated. And that distance problem is the first thing worth sitting with. 2.4 billion miles farther than predicted. To put that in human terms, if you drove at highway speed, 60 miles per hour, 24 hours a day, 7 days a week, non-stop, it would take you over 4,500 years just to cover that extra distance. That's the margin of error in humanity's model of its own solar system's edge, not the edge of some distant galaxy we barely understand. Our edge, the boundary of the place we live. We were off by 4,500 years of driving. Now, why does this matter beyond the obvious embarrassment to the models? It matters because the heliosphere isn't just a curiosity, it's a shield. One of the primary functions of the heliosphere is to deflect galactic cosmic rays, high-energy particles accelerated by distant supernovae and other extreme events across the galaxy. These particles are ionizing radiation. They damage DNA. They can affect atmospheric chemistry. The size and shape of the heliosphere determines how much of this radiation gets through to the inner solar system, to Earth, to us. If our model of the heliosphere was wrong by 20 to 30% in terms of distance, what does that mean for our models of cosmic ray exposure? What does it mean for long-duration space travel? What does it mean for understanding how life on Earth has been shaped by our position in the galaxy over billions of years? These are not small questions. They unfold from a single error, one that we only caught because two aging spacecraft accidentally survived long enough to measure the truth. And it wasn't just the distance that surprised us. The shape was wrong too. For years, the leading model pictured the heliosphere as comet-shaped, a blunt leading edge, facing the direction the sun moves through the galaxy, and a long trailing tail stretching out behind. That model held for decades. It seemed physically intuitive. Wind hitting a bubble should push the leading side in and let the trailing side stretch. Except that's not what the data shows. More recent analysis, informed partly by Voyager and partly by data from the IBEX mission, the Interstellar Boundary Explorer, points towards something radically different. Something that has been described, genuinely, in published scientific papers as a deflated croissant, squashed on both sides, rounded at the leading edge, and without the long trailing tail the models predicted. The shape of our solar system's protective bubble looks nothing like the diagrams in the textbooks. 7 major anomalies came out of Voyager's crossing of the heliopause. 7 things that weren't supposed to be there. A magnetic highway, cosmic shockwaves leaking outward into the galaxy, plasma cooler than predicted at the termination shock, magnetic field lines aligned in a direction that broke the models, a boundary that crosses and recrosses rather than holding a fixed position, bidirectional particle flows that suggested the boundary was permeable. And then, in 2025, the wall of fire, a ring of plasma at 30,000 to 50,000 Kelvin sitting at the heliopause, driven by magnetic reconnection, redefining the boundary as an active, energetic interface rather than a passive threshold. Each one of those anomalies is a story, and each one is a thread in the same larger revelation that the boundary of our solar system is not a fixed edge. It's a dynamic, asymmetric, permeable interface, and we fundamentally misunderstood it. That's what Voyager found. Not just data, not just numbers, a correction. the biggest correction to our model of our own cosmic neighborhood that we've ever had to make. And we're still making it. Before we can understand what Voyager found, we need to understand what Voyager is, where it came from, what it was designed to do, and why the fact that it made these discoveries at all is, in itself, one of the strangest stories in the history of exploration. Because here's the thing, Voyager wasn't supposed to survive long enough to find any of this. The mission was never designed to reach the heliopause. The instruments weren't chosen for interstellar science. The engineers who built it expected to be long retired before the spacecraft even got close to the boundary. And yet that old machine built with less computing power than your thermostat kept moving, kept transmitting, kept finding things that weren't supposed to be there. How that happened and what it means for everything we thought we knew, that's where this story really begins. Part 2, Built to Fail, 1977. On August 20th, 1977, a Titangent Centaur rocket lifted off from Cape Canaveral in Florida. 16 days later, on September 5th, a second one followed it. These were Voyager 2 and Voyager 1, respectively named in order of launch but destined to swap positions in space within months. The names would end up reversed in a way that was perfectly fitting for a mission that would spend the next 5 decades defying the logic of what was planned. The plan was simple, ambitious by the standards of the era, but simple. Voyager 1 and 2 were designed for a 5-year mission. They would fly past Jupiter, they would swing past Saturn, they would collect data, transmit images, and then that was it. Their work would be done. The mission would end. The spacecraft would drift on into the outer solar system, slowly losing power, slowly going quiet, eventually becoming silent metal in the dark. No one expected them to be alive in the 1990s, let alone in 2026. The hardware reflected that expectation. Each Voyager carries roughly 68 kilobytes of onboard memory. To put that into perspective, a single low-resolution photograph on your phone might be 200 times larger. A single second of audio from a streaming service would overflow Voyager's memory dozens of times over. The primary transmitter outputs about 23 watts of power. Your microwave oven uses somewhere around 1,000 watts. The signal from Voyager 1, traveling at the speed of light across more than 23 billion miles, arrives at Earth with a power of roughly 10 to the negative 17 watts. That's 0.00000000000000001 watts. Scientists have compared it to the energy of a snowflake hitting the ground, and we receive it, we understand it, we turn it into science. When the spacecraft launched, each was powered by 3 radioisotope thermoelectric generators, RTGs. These are essentially nuclear batteries. They convert the heat from the radioactive decay of plutonium-238 into electricity. At launch, each spacecraft was generating around 470 watts, but radioactive decay is constant. The power drops by roughly 4 watts per year. By 2026, Voyager 1 is producing something in the range of 40 watts. By 2030, it may not have enough power to run a single science instrument. The engineers who designed it gave it a lifespan measured in planetary flybys. The universe gave it a lifespan measured in generations. The instrumentation was chosen accordingly. The cameras, the plasma instruments, the magnetometers, the low-energy charged particle detectors. These tools were designed to study planets, their atmospheres, their magnetic fields, their moons. They were not chosen with the interstellar medium in mind. Nobody sat down in 1972 and said, let's make sure these can measure the density of plasma between the stars. That was not part of the design brief. And yet, almost by accident, several of them turned out to be exactly what was needed to characterize the boundary of the heliosphere. The plasma science instrument on Voyager 2, for instance, a device meant to measure the solar wind flowing past Saturn, would end up being the crucial tool that confirmed interstellar plasma density when the spacecraft crossed the heliopause in 2018. On Voyager 1, that same instrument failed in 1980, before the spacecraft even reached Saturn's closest approach. The fact that Voyager 2 still had a functioning plasma instrument at the heliopause crossing 41 years into a 5-year mission is not engineering. It's something closer to luck, or to the particular stubbornness of machines that were built, above all else, to be simple. That simplicity was a deliberate philosophy. The teams who built Voyager operated under a principle of redundancy and minimalism, backup systems for backup systems, circuits that could be rerouted in case of failure, software that could be updated from Earth, slowly and carefully, across distances that made the signal lag hours long. This philosophy was not glamorous. It was not the stuff of science fiction, but it meant that when components began to fail, and they did, one by one, across the decades, the spacecraft could be reconfigured, coaxed, and kept alive in ways no one had planned for. There's something in that story that connects directly to why we know what we know about the heliopause today. The only reason we have direct measurements of interstellar space is because a mission that should have ended in 1982 accidentally outlived its designers, its launch team, most of the engineers who built it, and nearly every assumption that went into it. The boundary we discovered was discovered by machines that weren't designed to find it. That's not a footnote. That's the central irony of the entire Voyager story. And as we'll see, the boundary itself turns out to have a similar character. Not what it was supposed to be, not what anyone planned for, but real and present and irreducibly strange. There was one more thing working in Voyager's favor, at launch a coincidence of celestial mechanics that comes around only once every 176 years. The alignment of the outer planets. Part 3. The grand tour that should have been the end. In the early 1960s, a graduate student at Caltech named Gary Flandreau calculated something remarkable. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would be aligned in a configuration that made it possible to visit all four in a single mission using each planet's gravity to slingshot a spacecraft to the next, a technique called gravity assist. This alignment would not recur until the 2150s. If NASA didn't fly in the window between 1977 and 1979, the opportunity was gone for over a century. They flew. Voyager 1 reached Jupiter in March of 1979 and returned images that stunned every scientist who saw them. Jupiter's Great Red Spot was revealed as a structure of extraordinary complexity. Its moon Io was discovered to be the most volcanically active body in the solar system, the first active volcanism ever detected beyond Earth. Europa's surface was a maze of fractured ice, suggesting a liquid water ocean beneath. These were not expected. These were not in the models. Even at Jupiter, not at the edge of the solar system, but at the fifth planet from the Sun, Voyager was already rewriting the science. Saturn followed. The rings, previously known but poorly resolved, turned out to be thousands of individual ringlets, braided and structured in ways that still aren't fully explained. Titan, Saturn's largest moon, was swathed in a thick nitrogen atmosphere denser than Earth's, another thing the models didn't predict. Voyager 1 was deflected north after Saturn, exiting the plane of the solar system and heading toward the heliopause on a steep upward trajectory. Its planetary science was done. Voyager 2 continued. Uranus in January 1986. Miranda, one of its moons, showed canyon walls 10 times taller than the Grand Canyon, geologic features that had no business existing on a body that small. Neptune in August 1989. A world of the deepest blue, with winds measured at over 2,000 kilometers per hour, faster than any winds ever recorded on any planet. And Triton, Neptune's moon, showed active geysers erupting nitrogen into a near-vacuum atmosphere. At each planet the pattern repeated. The models were incomplete, the reality was stranger, and Voyager delivered images that no amount of telescopic observation had prepared anyone for. By 1989, the planetary mission was complete, and this is the moment that matters most to the central story of what Voyager would eventually find, because from this point forward, everything was extra. Every additional day of operation, every additional transmission, every additional measurement was data the mission was never designed to collect. The spacecraft had already succeeded. They had already justified their existence. What came next was something else entirely. An accidental mission to the boundary of the solar system conducted by hardware that was never meant to go there. Part 4, The Last Photograph. In February of 1990, Voyager 1 was about 6 billion kilometers from Earth, traveling outward at about 17 kilometers per second. The cameras were still working, the power budget still allowed for their use, and someone, primarily Carl Sagan, advocating fiercely for it, convinced NASA to turn them back toward home. The resulting image is called the pale blue dot. Earth appears in it as a tiny point of light, barely distinguishable from noise, suspended in a ray of scattered sunlight. The whole planet, every war, every civilization, every mountain range, every ocean, reduced to a fraction of a single pixel. Sagan wrote words about that image that are still read at funerals and graduations, and the kinds of quiet moments when humans remember how temporary everything is. But what matters for this story isn't the poetry, it's what happened next. After that photograph was taken, the cameras were turned off permanently, not because they stopped working, because they cost power. Power the spacecraft no longer had to spare. The decision was deliberate and irreversible. After 1990, Voyager 1 would never take another picture. Looking back was done. From that point forward, there was only outward. This is the symbolic turn in the Voyager story, the moment it shifted from planetary mission to boundary mission. The cameras going dark meant the instruments that remained, the magnetometers, the plasma detectors, the cosmic ray counters, the low-energy particle instruments, were now all that Voyager had to offer the world. And those instruments, as it turned out, were exactly what was needed to answer a question no one had thought to ask in 1977. What does the edge of the solar system actually look like from the inside? The pale blue dot was the last moment we thought we understood our place. Everything after it would be a slow accumulation of evidence that we'd been wrong about the boundary we lived inside. The boundary we thought we understood. The boundary that, as the spacecraft drifted outward through the 1990s and into the 2000s, was getting closer and stranger with every passing year. Part 5. The first crack in the model. Before a spacecraft can reach the heliopause, it has to cross something called the termination shock, and the termination shock is where the model first began to show its cracks. Here's the physics, as plainly as it can be stated. The solar wind streams outward from the sun at supersonic speeds, typically between 400 and 800 kilometers per second. It's moving faster than the speed of sound in that medium, but as it travels farther from the sun, it weakens. The interstellar medium pushes back against it, and at some point, the solar wind slows abruptly from supersonic to subsonic. This is the termination shock, the inner boundary of the heliosheath, the turbulent region between the termination shock and the heliopause itself. Think of it like the edge of a jet of water from a faucet hitting a flat surface. There's a point where the flow suddenly slows and spreads. That's the termination shock. Models predicted it would sit at around 80 to 90 astronomical units. And here's where the first anomaly appeared. Voyager 1 crossed the termination shock in December of 2004 at approximately 94 astronomical units. Voyager 2 crossed it in August of 2007 at approximately 84 astronomical units. Those two crossings happened in different directions. Voyager 1 heading north of the ecliptic plane, Voyager 2 staying closer to it, and they crossed the same boundary at positions 10 astronomical units apart. 10 astronomical units is roughly the distance between Saturn and the Sun. That is not a small discrepancy. That is the difference between a sphere and something considerably more complicated. The termination shock isn't a uniform shell. It's lumpy, asymmetric, pushed inward in some directions and extended in others by the pressure of the interstellar medium flowing against it. And there's more. Voyager 2's crossing wasn't a single event. The spacecraft crossed the termination shock multiple times, moving outward through it, then apparently being pushed back inward as the boundary shifted, then crossing outward again. The boundary was sloshing. Like a tide, the heliosphere was breathing. Then came the plasma measurements, and these were genuinely surprising. The solar wind at the termination shock was cooler than predicted, significantly cooler. The models had assumed that when the solar wind slowed at the termination shock, its kinetic energy would convert to heat, the kind of thermodynamic behavior you'd expect from a shock wave. But the temperature increase observed was far smaller than it should have been. The energy was going somewhere else, into accelerated cosmic rays, it turned out. The particles were being energized rather than simply heated. The termination shock was a particle accelerator, behaving in ways the standard models of shock physics hadn't fully accounted for. What this told scientists was that the heliosheath, the region between the termination shock and the heliopause, was far more complex than anyone had modeled. It wasn't a simple buffer zone of slowed solar wind. It was a turbulent, asymmetric, particle-rich environment where energy moved in unexpected directions. And if the inner boundary was this complicated, what would the outer one, the heliopause, look like? We were measuring our own front door from the inside, and we were getting measurements that didn't match the blueprints. The real revelation was still a few years away. But the cracks in the model were widening, and somewhere in the heliosheath, moving outward at 17 kilometers per second, Voyager 1 was approaching something that would break the models entirely. Part 6. The Magnetic Highway. In late July of 2012, something unusual began happening to the data streaming back from Voyager 1. The instruments that measure charged particles, specifically the ones tracking low-energy particles originating from the Sun and high-energy galactic cosmic rays coming from outside the solar system, began recording a simultaneous shift. Solar particles were decreasing. Galactic particles were increasing, steeply, suddenly, in a way that looked like a transition zone rather than a gradual fade. But here's what made this genuinely strange. The magnetic field wasn't rotating. Every model of the heliopause predicted a magnetic field rotation at the boundary. Inside the heliosphere, the Sun's magnetic field is organized in a particular direction. Outside the heliosphere, the galactic magnetic field has its own orientation. At the boundary, you should see the field flip a clear, measurable rotation that marks the transition from one magnetic domain to the other. It's one of the most fundamental predictions of heliospheric physics. And in late July of 2012, Voyager 1 was seeing particle flux consistent with crossing the heliopause but no magnetic rotation. None. The magnetic field was steady, continuous, as if the spacecraft hadn't crossed anything at all. What was happening? What Voyager 1 had entered, and this took time to understand, was something that now goes by the name the magnetic highway, a region where the magnetic field lines of the Sun and the galaxy were connecting and aligning, not rotating against each other, but merging. In a process called magnetic reconnection, field lines from the two different domains were linking up and reorganizing, and along those connected field lines, particles were flowing in both directions simultaneously. Solar particles were flowing outward along the connected lines, escaping into interstellar space. Galactic cosmic rays were flowing inward along the same lines, penetrating deeper into the heliosphere than they should have been able to. The heliopause wasn't a wall. It was a highway. No classical model of the heliosphere had predicted this. The standard picture was of a fairly clean boundary, a surface where the two magnetic domains met and the field rotated across it. What Voyager 1 found was a zone of interpenetration, a region where the two domains weren't just meeting, they were actively mixing, where particles from inside and outside the heliosphere were exchanging places through aligned and reconnected magnetic field lines. The implications of this are significant. If the heliopause is permeable, if galactic cosmic rays can flow inward through connected magnetic field lines rather than being deflected, then the heliosphere provides less shielding than the models assumed. The boundary that was supposed to protect the inner solar system from galactic radiation is, at least in places, more porous than a wall. It's more like a membrane, one with channels. This also raised a deeper question about cosmic ray exposure in the inner solar system. The standard assumption was that the heliopause deflects the majority of high-energy galactic particles. If that assumption is flawed, if there are magnetic highways through which radiation can travel inward, then every calculation of cosmic ray exposure on Earth, every model of how galactic radiation has influenced biological evolution, every estimate of radiation doses for deep space travelers needs to account for this permeability. The homework, as it were, needs to be redone, and the magnetic highway told us something else. The boundary is dynamic. It's not a static membrane. It's an active zone of reconnection and particle exchange, driven by the continuous interaction between the solar magnetic field and the galactic magnetic field. The heliosphere isn't just sitting there being a shield, it's constantly negotiating with the galaxy around it, and we had no idea. But here's the thing: Voyager 1 was in the magnetic highway, watching these particle fluxes shift, and the magnetic field still wasn't rotating, which meant scientists couldn't be sure whether the spacecraft had actually crossed the heliopause or was in some transitional zone just inside it. The debate got heated. Some researchers argued Voyager was still in the heliosphere. Others argued the particle data was conclusive, and then, in August of 2012, the data resolved the question, though not in the way anyone expected. Part 7. The crossing that wasn't a crossing. August 25, 2012, Voyager 1 was approximately 121 astronomical units from the Sun, about 11.2 billion miles. 11.2 billion miles from home. And on that date, the plasma density around the spacecraft jumped by a factor of roughly 80. In one measurement period, the number of electrons per cubic centimeter went from about 0.001 to about 0.08, 80 times denser. The solar wind plasma had effectively vanished, replaced by something denser and colder, the plasma of the interstellar medium. This was the crossing, not the particle fluxes in late July, which had been ambiguous, not the magnetic highway, which had been unprecedented. The plasma density jump was unambiguous. Voyager 1 had left the heliosphere. Except, and this is the part that caused months of debate, the magnetic field still hadn't rotated significantly. The models said it should. The models said that when you cross the heliopause, the magnetic field direction should change substantially, reflecting the transition from the solar magnetic field to the galactic magnetic field. Voyager 1 measured a change of only a few degrees. That was not what anyone predicted. The scientific community had to reconcile two apparently contradictory facts. The plasma density was unambiguously that of interstellar space, but the magnetic field was nearly continuous with what it had been inside the heliosphere. How do you cross the most significant boundary in the solar system without the magnetic field noticing? The answer, it turns out, is that the local interstellar magnetic field in the particular direction Voyager 1 happened to be traveling is nearly aligned with the Sun's magnetic field. This wasn't predicted. Models of the galactic magnetic field in our solar neighborhood assumed it would be oriented at a significant angle to the heliosphere. But in the direction of Voyager 1's travel, the two fields happened to be nearly parallel. So crossing the heliopause in that direction produces almost no field rotation, not because the boundary isn't there, but because the two sides of the boundary happen to be magnetically aligned in that location. This was not a coincidence that anyone had built into the models. It suggested that the local interstellar medium, the region of gas and magnetic field immediately surrounding our solar system, is structured and organized in ways that existing models hadn't captured. The galaxy around our neighborhood is not uniform. It's shaped and directed in specific ways that affect how the heliosphere interacts with its surroundings. And we only discovered this because Voyager 1 crossed the heliopause at exactly the right direction and the right time to reveal it. The crossing also revealed something about the scale of the transition. It wasn't instantaneous. Voyager 1 had been watching particle fluxes shift for weeks before the plasma density jumped. The magnetic highway phase lasted for a month. The overall transition zone was tens of astronomical units wide in places. This wasn't like crossing a river with defined banks. It was more like walking into fog, gradual in some dimensions, abrupt in others, and deeply dependent on which direction you were traveling. For the first time in history, a human-made object was in interstellar space, not inferred, not calculated, measured directly. And the measurement said, everything we thought we knew about the shape, behavior, and character of this boundary needs revision. That was Voyager 1. 6 years later, Voyager 2 crossed the same boundary and confirmed everything while complicating it further. Part 8, Voyager 2, confirms and complicates. November 5th, 2018. Voyager 2 was approximately 119 astronomical units from the Sun, travelling in a completely different direction from Voyager 1, roughly 30 degrees south of the ecliptic plane. And in a single day, its plasma science instrument, the one that had been working for 41 years, the one that failed on Voyager 1 in 1980, recorded a sharp, decisive increase in plasma density. Interstellar plasma. The crossing was cleaner than Voyager 1's in some ways, more ambiguous in others. The sharpness of the density increase was striking. Where Voyager 1's crossing had elements of gradualness, the weeks of particle flux transition, the magnetic highway phase Voyager 2's plasma jump was sharper. The boundary in Voyager 2's direction appeared to be thinner, more defined, which makes sense if the heliosphere is asymmetric. If the boundary is pushed closer to the Sun in some directions by the interstellar medium's pressure, and the compressed boundary would be thinner and more abrupt. But Voyager 2 also detected something Voyager 1 couldn't measure, a magnetic field rotation. Small, only a few degrees, but measurable. A genuine change in field direction as it crossed the heliopause. This confirmed that the near-zero rotation Voyager 1 saw was a local feature, not a universal property of the heliopause. In Voyager 2's direction of travel, the galactic magnetic field was oriented slightly differently, and the crossing produced a detectable signature. What both crossings together tell us is that the heliopause is not a uniform surface. It behaves differently in different directions. Its thickness, its sharpness, its magnetic structure, all of these vary depending on where you are on the boundary. The heliosphere is shaped by the interplay between the solar wind pressure from inside and the interstellar medium pressure from outside, and that interplay is not the same in all directions. The heliosphere is squashed, asymmetric, and locally variable in ways that no single point measurement could have revealed. And this is what makes the dual spacecraft mission so important in retrospect. With only one Voyager, we might have thought our measurement was universal. With two, separated by over 20 degrees in ecliptic latitude and travelling in different directions, we can see that the boundary varies. The heliopause is an irregular surface, a lumpy, shifting, directionally variable interface between our solar system and the galaxy. And the variation between Voyager 1's crossing and Voyager 2's crossing is probably just the beginning of the complexity. There are directions we haven't measured at all. By 2018, both Voyagers were in interstellar space, and the picture that had emerged from their combined data was clear enough. The heliosphere looks nothing like the textbook version, nothing at all. But the anomalies didn't stop at the boundary crossings. The data continued to produce surprises, and some of the biggest ones came from looking at the shape of the heliosphere itself. Part 9. The shape of the solar system is wrong. For most of the 20th century, if you asked an astrophysicist to draw the heliosphere, they would have drawn something roughly like a comet, a round leading edge on the side facing the direction the sun moves through the galaxy. A long, streaming tail on the opposite side, trailing behind. The logic was simple and intuitive. The sun moves through the interstellar medium at about 26 kilometers per second. The interstellar medium pushes back. The side facing the flow gets compressed. The side facing away gets stretched. A comet shape, simple, clean, wrong. The evidence for a fundamentally different shape has been accumulating over the past decade, drawing on data from Voyager and from the IBEX mission, a small NASA spacecraft that maps the boundary of the heliosphere by detecting energetic neutral atoms. These are atoms that bounce off the boundary and return inward, carrying information about what they hit. IBEX has been building a global picture of the heliosphere's shape from the inside, and what it shows combined with the Voyager in situ measurements points to something radically different from the comet model. The current best model is sometimes called the deflated croissant. That's not a casual description, it comes from the modeling work of physicists who ran simulations incorporating a crucial physical process the older models had underestimated: pickup ions. Pickup ions are created when neutral atoms from the interstellar medium drift into the heliosphere, get ionized by solar ultraviolet radiation or charge exchange, and are suddenly swept up by the solar wind. They carry a lot of energy, much more energy, proportionally, than the thermal solar wind particles around them, and a substantial fraction of them, rather than being fully incorporated into the solar wind, escape back toward the heliopause and beyond. They leak out of the system. They carry energy with them as they go. This leakage reduces the internal pressure of the heliosphere in a way that the older models didn't account for. Less internal pressure means the heliosphere can't inflate as far in the trailing direction. The long cometary tail gets suppressed. The shape compresses, especially on the sides. Instead of a comet, you get something more like a rounded sphere that's been squashed on two sides, a shape that astronomers and heliophysicists have ended up calling, without apparent embarrassment, a deflated croissant. If this shape is correct, and the evidence increasingly supports it, then the heliosphere is considerably more compact than the comet model suggested. There is no vast trailing tail extending dozens or hundreds of astronomical units behind the sun's direction of travel. The protection the heliosphere provides varies significantly by direction. In the compressed sides, the boundary may be closer to the inner solar system than the leading edge suggests. Cosmic rays approaching from those directions may encounter less shielding. And here's where this connects back to something that should give us pause. The heliosphere is our shield. It's the thing standing between the inner solar system and the full flux of galactic cosmic rays. If its shape is wrong, then our understanding of how much shielding we receive and from which directions is also wrong. The entire history of Earth's exposure to cosmic radiation, which has played a role in climate, atmospheric chemistry, and potentially biological mutation rates, has been calculated based on a model of the heliosphere that turns out to be inaccurate. We're going to need to redo those calculations. We're still doing them. Part 10. Solar storms. Escape the solar system. Here is something that should feel impossible. A solar storm erupts on the surface of the sun, not a small one, a coronal mass ejection, which is among the most energetic events our star produces. Billions of tons of magnetized plasma hurled outward at speeds of 1 to 3 million kilometers per hour in a wave of charged particles and tangled magnetic field lines that expands as it travels, like a bubble being inflated at extraordinary speed. These events happen regularly. We track them. We warn satellites and power grid operators when large ones are heading toward Earth. We understand them reasonably well within the inner solar system. But here's what the models didn't account for. That coronal mass ejection doesn't stop at Earth. It doesn't stop at Mars. It keeps going past the asteroid belt, past Jupiter, past Saturn, past Uranus, past Neptune, past the orbit of Pluto and every other object we've named and catalogued in the outer solar system. It reaches the termination shock the inner boundary of the heliosphere, where the solar wind slows from supersonic to subsonic and crosses it. It moves through the heliosheath, that turbulent buffer zone of slowed solar wind, for billions of additional kilometers. It reaches the heliopause, the outermost boundary of the sun's influence, the place where interstellar space begins. And then, according to data returned by Voyager 1, it doesn't stop there either. The shockwave from that solar eruption propagates into interstellar space. It crosses the heliopause and keeps going, rippling outward through the plasma of the local interstellar medium, producing measurable oscillations in the charged gas between the stars, detectable by instruments 11 billion miles from where the eruption started, on a spacecraft with 68 kilobytes of memory and a transmitter running on 23 watts of power. The sun does not stop at its own boundary. The sun influences interstellar space. Voyager 1 detected these propagating shock waves in 2012 and 2014. What it recorded were plasma oscillations, rhythmic compressions and expansions in the density of the interstellar plasma just beyond the heliopause. Scientists traced them backward through time using known propagation speeds and matched them to specific coronal mass ejections that had left the sun months and years earlier. The signal chain, when you lay it out in full, is almost difficult to believe. A magnetic eruption on the surface of a star, a shockwave that spends months crossing the full width of the solar system, a crossing of the boundary that was supposed to contain everything, and then a ringing like a bell being struck in the plasma of the interstellar medium, recorded by a machine built in the mid-1970s that was designed for a 5-year mission and was, at the time of these detections, 35 years into that 5-year mission. The fact that we can even verify this is worth a moment of appreciation. We could trace the oscillation Voyager detected back to the original solar event because we have continuous solar monitoring going back decades. We know when specific coronal mass ejections occurred and how fast they were traveling. When Voyager's plasma wave instrument recorded an oscillation in the interstellar medium, scientists could calculate backward accounting for the travel time across the heliosphere, accounting for the propagation speed of the shockwave through the interstellar medium, and point to a specific eruption on the sun as the source. The whole chain of evidence is there. It's not inferred loosely. It's reconstructed precisely, and it tells us something about the heliopause that our models had completely failed to capture. The heliopause is not a containment system. This was the assumption, stated or unstated, in virtually every heliospheric model prior to Voyager's interstellar crossing. The idea was that the sun's influence, its wind, its magnetic field, its energetic events was bounded, contained within the heliosphere, and that the interstellar medium, on the other side of the boundary, was a separate domain, governed by its own physics, largely unaffected by whatever our star was doing. The boundary was conceived as a kind of cosmic membrane, permeable, perhaps to the most energetic galactic particles coming inward, but fundamentally separating two different physical environments. Inside, the sun's domain. Outside, the galaxy's domain. What Voyager showed is that the boundary leaks in both directions. Galactic cosmic rays can flow inward through magnetically connected field lines, the magnetic highway we discussed earlier, and solar shockwaves can propagate outward into the interstellar medium, carrying energy from the sun's surface into the space between the stars. The boundary doesn't bottle the sun up. It modulates the sun's influence, shapes it, slows it, but it doesn't stop it. Our solar system is less isolated than we thought. The heliosphere is less of a sealed container and more of a highly permeable, bidirectionally leaky interface between our star and the rest of the galaxy. Now sit with the scale of what that means. The Sun is 93 million miles from Earth. The heliopause is approximately 121 astronomical units from the Sun over 11 billion miles. And beyond that, the Sun's shock waves continue to propagate. We don't know how far. We've only ever had instruments right at the boundary. Voyager 1 and 2 are both within a few tens of astronomical units of the heliopause. They're sampling the interstellar medium at one location in two directions in the immediate vicinity of the crossing point. What the interstellar medium looks like, 50 astronomical units past the heliopause. Whether the solar influence fades to nothing in that distance or persists across hundreds of astronomical units is something we genuinely do not know. The interstellar medium, though extraordinarily thin by any earthly standard, is not empty. A single cubic centimetre of it contains roughly 0.1 electrons on average, compared to the roughly 10 million billion molecules per cubic centimetre of the air you're breathing right now. It is, by any practical measure, a near-perfect vacuum. But it is not nothing. It has structure. It has density variations regions of slightly higher or lower concentration that formed over millions of years from the combined influence of stellar winds, supernova remnants, and the large-scale rotation of the galaxy. It has magnetic field organization, threaded through it in directions that reflect the history of massive stellar events in our galactic neighborhood. And those structures, those density variations and magnetic channels can guide and sustain a propagating shockwave for a very long time. How long and how far, we cannot yet say. This is one of the most frustrating limitations of the Voyager program, and one worth naming honestly. We have two data points, two spacecraft, in two directions, right at the boundary. The heliosphere extends in every direction around the Sun, a full three-dimensional structure, and we have sampled it at 2 points at one distance, in one small region of one galactic neighborhood. Everything we know about the interstellar medium from direct measurement comes from those two data points. It is, given the constraints, a remarkable scientific achievement, but it is also an extraordinarily thin slice of evidence on which to build a comprehensive picture of how our solar system interacts with the galaxy around it. The honest answer to the question of how far the Sun's influence extends into interstellar space is, we don't know. Our best models suggest it fades relatively quickly past the heliopause, that the shock waves lose coherence as they propagate, that the interstellar medium disperses the energy and absorbs the disturbance within some tens of astronomical units. But those models are built on the same theoretical frameworks that placed the heliopause in the wrong location, gave it the wrong shape, missed the magnetic highway, and failed to predict the wall of fire. We have reasons to be humble about what the models tell us. What we do know, what Voyager confirmed directly, is that the Sun reaches beyond its own boundary. The storms on our star don't end at the edge of the solar system. They continue outward into the galaxy, imprinting themselves on the interstellar medium in measurable ways. The heliosphere is not a sealed room. It is a structure in continuous, bidirectional exchange with the universe around it. And that exchange, that permeability, that leaking in both directions, is one of the things that makes the boundary so much more interesting than the models had imagined. Our solar system is not isolated. It never was. We just didn't have the instruments close enough to see the connection until a 49-year-old spacecraft powered by the heat of decaying plutonium sent back the data that proved it. Part 11. The coincidence that broke physics expectations. Let's return to the magnetic field problem, because it's worth sitting with more carefully than the headline version of this story usually allows. When Voyager 1 crossed the heliopause in August of 2012, and found that the magnetic field direction barely changed, the initial reaction in the scientific community was not excitement, it was confusion. Genuine, uncomfortable confusion of the kind that doesn't make it into press releases. The particle data had been clear enough. Starting in late July, the counts of solar particles dropped sharply. The counts of galactic cosmic rays rose sharply. Both trends happened simultaneously and sustained themselves. This wasn't a fluctuation, it was a transition. And then on August 25th, the plasma density jumped by a factor of roughly 80 in a single measurement period, from the thin, hot, sparse plasma of the heliosheath to the denser, cooler plasma of the interstellar medium. That jump is about as unambiguous as planetary science gets. The spacecraft was in a different physical environment, but the magnetic field barely moved. A few degrees of rotation, at most, when the models predicted something far more substantial. And this created a problem that ran deeper than just a discrepancy in the numbers. It created a problem of interpretation, because the magnetic field rotation wasn't just a predicted feature, it was supposed to be the defining signature of the crossing, the confirmation, the thing that would let scientists say with certainty, yes, this is interstellar space, we can prove it by the field. Without a clear rotation, some researchers began arguing that Voyager 1 hadn't actually crossed the heliopause, that the plasma density jump was being misread, that the spacecraft was in some transitional zone, some previously unknown region, sitting between the heliosheath and true interstellar space that didn't fit any existing category in the models. The debate lasted months. Papers were written, counterpapers were written. The team most closely associated with the plasma data argued the crossing was real. Researchers focused on the magnetic data argued for more caution. It was, in the way of genuine scientific disputes, a little messy and a little uncomfortable and entirely necessary, because the answer that eventually emerged from the analysis is, once you state it plainly, one of the more remarkable coincidences in the recent history of astrophysics. The galactic magnetic field in our local neighborhood, specifically in the direction Voyager 1 was traveling, roughly northward out of the ecliptic plane, happens to be nearly aligned with the Sun's magnetic field, within a few degrees. These are two completely different magnetic systems with completely different origins. The Sun's field is generated by its own internal dynamo, a process driven by convection and differential rotation inside the star. That field is organized by the structure of the heliosphere and shaped by the solar wind as it expands outward. The galactic magnetic field in this region of the Milky Way, by contrast, was shaped over millions and billions of years by the cumulative influence of stellar formation and death, supernova remnants, propagating outward and compressing the interstellar medium, the large-scale spiral structure of the galaxy, imposing its own organization on the gas and field threading through the disk. There is no physical reason, derivable from first principles, why those two fields should point in the same direction. The Sun doesn't know about the galactic field when it generates its own. The galactic field doesn't adjust itself based on what individual stars are doing. They are independent systems operating on completely different scales, driven by completely different physics, and yet, in the direction Voyager 1 happened to be traveling, they are aligned within a few degrees. You could call it lucky. You could call it a coincidence. What you cannot call it is predicted, because no model of the heliopause prior to Voyager's crossing incorporated this alignment as a possibility worth accounting for. And here is where Voyager 2 becomes indispensable to the story. When Voyager 2 crossed the heliopause in November of 2018, it was traveling in a fundamentally different direction roughly southward of the ecliptic plane, about 30 degrees away from Voyager 1's trajectory. And in that direction, the magnetic field did rotate, not dramatically. Voyager 2 measured a small but definitive change in field direction as it crossed the boundary, a few degrees, but real, measurable, consistent with a transition between two magnetic domains that are not perfectly aligned. That single data point, the contrast between Voyager 1's near-zero rotation and Voyager 2's detectable rotation in two different crossing directions, tells us something fundamental about the structure of the space surrounding our solar system. The magnetic alignment between the solar field and the galactic field is not a universal property of the heliopause. It is a local feature, direction-dependent. In the Voyager 1 direction, the fields happen to align. In the Voyager 2 direction, they don't align as closely, which means the local interstellar medium, the gas and field surrounding our solar system, is not magnetically uniform. It has structure. Its field points in one direction in some places and slightly different directions in others, varying over scales comparable to the size of the heliosphere itself. This has direct consequences for how cosmic rays move through the boundary, and therefore how much radiation the inner solar system receives and from which directions. Cosmic rays are not like light. They don't travel in straight lines. They are charged particles, and charged particles in a magnetic field follow curved paths. They spiral along field lines. They scatter when they encounter irregularities in the field. The efficiency with which a cosmic ray can penetrate the heliopause and travel inward toward Earth depends on the geometry of the magnetic field at the point of entry. Where the galactic field and the solar field are aligned, where the magnetic highway forms, cosmic rays can flow inward with less resistance. Where the fields are misaligned, there is more deflection, more scattering, more shielding. What this means practically is that the cosmic ray environment inside the heliosphere is not uniform. The radiation climate of the inner solar system, the background flux of high-energy galactic particles that reaches Earth, is not the same from all directions. It depends on the magnetic structure of the boundary in each direction, and that structure, as Voyager showed us, varies, which means that every model of cosmic ray flux at Earth that assumed a uniform, direction-independent, heliospheric shield needs to be revisited. Not thrown out, the corrections may be relatively small in terms of absolute dose, but revisited because the assumption of uniformity was wrong. There's a longer timescale implication here as well. The Sun moves through the galaxy at about 26 kilometers per second, tracing a slow orbit around the galactic center over hundreds of millions of years. As it moves, the local interstellar medium it encounters changes. The magnetic field structure of the interstellar medium in different regions of the galaxy varies, shaped by different histories of stellar activity, different supernova remnants, different density clouds. As the Sun moves through these different environments, the alignment between its magnetic field and the surrounding galactic field will change. Sometimes the fields will be more aligned, the magnetic highway effect will be stronger, cosmic ray penetration will be more efficient. Sometimes they'll be less aligned, the shielding will be more effective, cosmic ray flux inside the heliosphere will be lower. This variation, playing out over millions of years, may leave detectable traces in Earth's geological record, in isotope ratios, in cosmic ray-produced nuclides preserved in ice cores and sedimentary rocks, in the very subtle fingerprints of radiation exposure written into the chemistry of life over deep time. We are not at a point where we can read that record cleanly. The connection between the magnetic structure of the local interstellar medium and the long-term cosmic ray climate of Earth is real, but difficult to quantify with the data we have. What Voyager gave us is the first direct evidence that the boundary is magnetically non-uniform, that the shield varies by direction, and that is the foundation on which those longer-term questions can start to be addressed. What Voyager revealed about the magnetic alignment problem is not just a correction to heliospheric physics in the narrow sense. It is a window into the structure of the local interstellar medium, the specific region of the galaxy our solar system currently occupies, a warm, relatively low-density bubble called the local interstellar cloud, itself embedded in a larger structure called the local bubble, a region of hot, thin gas carved out by ancient supernovae. That environment has a history. It has a magnetic geometry shaped by that history. And we are only now, with 2 aging spacecraft at the boundary, beginning to read the first lines of it. The local interstellar medium is not a featureless backdrop. It is an organized environment with structure on scales comparable to the heliosphere, and that structure shapes the boundary we live inside in ways we are still mapping. The mapping is incomplete. It will remain incomplete for a long time, because the instruments doing the mapping are dying. And yet what they've already told us, that the boundary is magnetically variable, direction dependent, structured by a galactic field with its own complex history, is enough to fundamentally change how we think about our solar system's place in the galaxy. We thought we lived in a bubble with uniform walls. Voyager showed us the walls are patchwork, and the patches are the galaxy's fingerprints. Part 12, The Wall of Fire, 2025. In June of 2025, a paper appeared in the astrophysical literature that most people outside of heliospheric physics probably missed entirely. It didn't make the front page of many science news websites. It didn't generate the kind of breathless coverage that a Mars landing or a new exoplanet discovery tends to attract. But inside the community of researchers who study the boundary of the solar system, it generated significant discussion, the kind of careful, serious attention that scientists give to findings that force them to reconsider something they thought was settled. The paper reanalyzed archival data from both Voyager spacecraft, combining those measurements with updated models of magnetic reconnection at the heliopause. And what it found, sitting in data that had been collected years or even decades earlier and waiting for the right analytical framework to reveal it, was this. At the heliopause, right at the boundary between the solar system and interstellar space, there appears to be a layer of plasma heated to temperatures between 30,000 and 50,000 Kelvin, not distributed throughout the heliosphere, not spread across the helio sheath, specifically at the boundary itself, a thin, energetic shell of superheated plasma sitting precisely at the interface where our solar system ends and the galaxy begins. The science communication world, which has a reasonable appetite for dramatic nomenclature, quickly started calling it the Wall of Fire. The scientists involved in the research are more careful with their language, as scientists tend to be, and as they should be, because precision matters when you're describing something genuinely new. But the nickname stuck, and honestly it's not entirely unfair. There is something sitting at the edge of the solar system that is burning at temperatures nobody predicted. Whatever you want to call it, that is a real and remarkable thing. Let's be clear about what this feature is not before we talk about what it is. The plasma at 50,000 Kelvin in this boundary layer is extraordinarily thin. We're talking about a region of space where the particle density is already far below anything we would consider a vacuum on Earth. The number of particles per cubic centimeter at the heliopause is a small fraction of 1, meaning that on average, a cubic centimeter of space at the boundary contains less than 1 particle. At those densities, temperature is a measure of how fast individual particles are moving, not how much total energy is present in a given volume. A particle moving at the speed corresponding to 50,000 Kelvin carries significant kinetic energy individually, but there are so few of them per unit volume that the total energy density is low. A spacecraft passing through this region as Voyager did would not be physically damaged by it. It would not melt. It would not be detected as heat in any meaningful engineering sense. The Wall of Fire is energetically extreme at the particle level and physically harmless at the engineering level. It's not dangerous, but it is extraordinary, and the distinction between those two things matters for understanding why. What creates it is magnetic reconnection. We've talked about reconnection in the context of the magnetic highway, the process by which solar and galactic magnetic field lines connect and align, creating channels through which particles can flow in both directions across the boundary. Reconnection is the same physical process here, but in a slightly different configuration and with a different primary outcome. At the heliopause, the solar magnetic field and the galactic magnetic field are in continuous contact. They push against each other, they interact, and in regions where the field lines are oriented in ways that allow it, they break apart and snap back together in new configurations, releasing the energy stored in the magnetic field as kinetic energy and heat. Think of it like this. Magnetic field lines under tension are a little like stretched rubber bands. When two rubber bands are pressed against each other with enough force, they can slip past each other and snap into a new configuration, releasing energy in the process. Magnetic reconnection is that snap happening continuously at the boundary of the heliosphere, wherever the geometry of the two fields allows it. The energy released goes partly into accelerating particles, which contributes to the cosmic ray and energetic particle populations we've already discussed, and partly into heating the local plasma. At the heliopause, the cumulative effect of continuous reconnection across the boundary surface appears to be enough to maintain a thin shell of plasma at temperatures between 30,000 and 50,000 Kelvin, continuously, as a steady-state feature of the boundary, not a transient event. Now let's put 50,000 Kelvin in context, because the number alone doesn't communicate much without a reference point. The surface of the Sun, the photosphere, the layer that produces the visible light we see, has a temperature of approximately 5,800 Kelvin. The wall of fire at the heliopause is roughly 8 to 9 times hotter than the visible surface of the Sun. That's the thing sitting at the edge of our solar system that nobody knew about until 2025. Something nearly 10 times hotter than the Sun's surface, wrapped around the boundary of the heliosphere like a shell. Now, before that comparison creates the wrong impression, the Sun's corona, its outer atmosphere, reaches temperatures of 1 to 3 million Kelvin, which makes 50,000 Kelvin look modest by comparison. The corona heating problem is one of the long-standing mysteries of solar physics. It should, by simple thermodynamic logic, be cooler than the surface below it, but it isn't, and the leading explanation involves again magnetic reconnection in the solar atmosphere, releasing energy into the coronal plasma. So reconnection heating at a boundary is not without precedent. What's striking about the heliopause case is not that the temperature is record-breaking in an absolute sense. It's that it exists at all in a location where the models predicted nothing remotely like it. Every model of the heliopause prior to this finding treated the boundary as essentially passive in thermal terms. A transition zone, yes. A region of changing particle populations and magnetic field structure, yes, but not a source of significant heating. Not a location where magnetic energy was being continuously converted into thermal energy at rates sufficient to maintain a multi-10,000 Kelvin plasma shell. The boundary was modelled as cold and quiet. It turns out to be warm and active. That's not a small revision. That's a different picture of what the heliopause is. And this is the point where the wall of fire stops being a standalone discovery and becomes another piece of the same larger story. Think about what we've established across this video. The heliopause is in the wrong location 20 to 30% farther from the Sun than predicted. Its shape is wrong, a deflated croissant rather than a comet. It's asymmetric, behaving differently in different directions. It's permeable, leaking galactic cosmic rays inward and solar shock waves outward simultaneously. It has a magnetic highway, a zone of field line connection that no model anticipated. Its magnetic structure varies by direction in ways that reflect the organization of the local interstellar medium. And now it has a wall of fire, a thin, continuously maintained shell of superheated plasma driven by continuous magnetic reconnection at the boundary surface. Every single one of those features points toward the same conclusion. The heliopause is not a passive surface. It is not a static membrane. It is an active, dynamic, energetically driven interface between two physical domains, the Sun's domain and the galaxy's domain, and it is in continuous negotiation between them. Energy flows across it in both directions. Particles flow across it in both directions. Magnetic field lines connect across it and disconnect and reconnect in an ongoing process that heats the boundary and channels radiation and links our solar system to the larger structure of the interstellar medium. The edge of our solar system is alive in the sense that it is constantly processing energy and constantly changing. It breathes, it burns, it channels, it leaks. 7 anomalies, 7 ways the models were wrong. And the question that naturally follows from all of them is whether 7 is the final count or just the beginning. We have 2 data points in 3-dimensional space, 2 spacecraft in 2 directions, at 1 distance from 1 star. The heliopause extends in every direction, shaped differently at every point, varying with the structure of the local interstellar medium in ways we are only beginning to characterize. How many more features are sitting in directions we haven't sampled? How many more things are happening at the boundary that we would see if we had instruments pointed elsewhere? How many wall of fire equivalents are embedded in archival data we haven't yet looked at with the right analytical tools? We don't know, and the instruments that could help us find out are dying. That's the tension at the center of the Voyager story right now. Just as our models are sophisticated enough to extract new discoveries from old data, just as the analytical frameworks are catching up to what the spacecraft actually measured, the spacecraft themselves are running out of time. The window for new measurements is closing. And when it closes, we will be left with 2 crossing points, 2 magnetic signatures, 1 wall of fire, and a boundary that we now know is far stranger than we imagined, but that we have barely begun to map. What happens after the instruments go silent and what Voyager keeps doing even then is the part of this story that nobody talks about enough. Part 13. The spacecraft begins to die, 2023 to 2036. In the summer of 2023, something went wrong with Voyager 1. The telemetry data streaming back to Earth, the housekeeping signal that reports on the spacecraft's internal state, the equivalent of a vital signs monitor, became garbled, not corrupted in a way that stopped transmission entirely. The signal was still arriving, the spacecraft was still talking, but what it was saying had become unreadable, a stream of data that looked superficially like normal telemetry but contained errors that made it impossible to interpret with confidence. The spacecraft was speaking. We just couldn't understand it anymore. Engineers at the Jet Propulsion Laboratory in Pasadena began working through the problem, and I want you to understand what that process actually looks like, because it's unlike any troubleshooting situation most of us will ever encounter. Voyager 1 is currently more than 23 billion kilometers from Earth. A radio signal, traveling at the speed of light, the fastest anything can travel, takes approximately 22 hours to reach the spacecraft from the ground. Another 22 hours for a response to return. Every single command sent to Voyager 1 requires a minimum of 44 hours before engineers can see whether it did anything. You cannot just try something and check the result. You cannot iterate quickly. You plan a command, you send it, and then you wait nearly 2 days to find out what happened. Then you plan the next step. This is the rhythm of working with Voyager. It has been the rhythm for decades. The engineers who do this work are accustomed to it in the way that you eventually become accustomed to any unusual constraint that defines your professional life. But in 2023, with the telemetry corrupted and the cause unknown, that 44-hour round trip wasn't just a constraint. It was the frame around every attempt to diagnose a problem on a spacecraft whose design documentation predates the careers of most of the people currently working on it. What they eventually determined, after months of careful analysis, was that a single memory chip in one of the flight data computers had failed. Not in a catastrophic way. The chip hadn't blown out, hadn't stopped receiving power, hadn't gone completely dark. It was still there, still nominally functional, still part of the computer's operation. but it was producing corrupted outputs. Somewhere in that chip, a small region of memory was no longer storing and returning data reliably, and the flight software that happened to be stored in that region was the software responsible for packaging the telemetry before transmission, which is why the signal arriving at Earth looked like signal, but wasn't. The solution the team developed is worth describing carefully, because it represents something genuinely remarkable in the history of spacecraft engineering. They could not replace the chip. They could not physically access the spacecraft. What they could do was relocate the affected software, move it out of the damaged region of memory and into other sections of the flight data computer that were still functioning correctly. The catch was that no single healthy section of memory was large enough to hold the entire software package, so they split it. They divided the code into segments, distributed those segments across multiple different memory locations, added new code to make sure the segments could find each other and operate as a coherent whole, and then across a communication link with a 44-hour round-trip delay, they uploaded the new configuration to a spacecraft 11 billion miles away. In April of 2024, it worked. Voyager 1 began sending coherent, readable telemetry again. Scientists and engineers on the team, some of whom have dedicated decades of their careers to this mission, reportedly cheered when the confirmation arrived. And they had earned that cheer. What they had done was the equivalent of performing open-heart surgery on a patient you can only communicate with by postal mail, and the patient is 11 billion miles away, and your surgical tools are radio waves, and the instruction manual for the surgery was written before most of the surgical team was born. The documentation that JPL engineers used to work on Voyager was written in the 1970s. The programming language the flight computers use is decades obsolete. The institutional knowledge of how the spacecraft actually behaves, the subtle quirks and behaviors that only emerge from decades of operation, exists partly in documents and partly in the memories of engineers who are themselves aging, some of whom have retired, some of whom have died. There is a generational knowledge transfer problem embedded in the Voyager program that doesn't get discussed much in the press coverage of the exciting discoveries. The people who know this spacecraft most deeply are not going to be around forever, and the spacecraft, in its own way, is outliving the community that understands it best. But the 2024 fix was not a recovery. It is important to be clear about that. It was a successful management of decline. The underlying trajectory of Voyager's capabilities is one of continuous, irreversible reduction. The power output of the radioisotope thermoelectric generators drops by roughly 4 watts per year as the plutonium-238 decays. That process cannot be stopped or reversed. It is the physics of radioactive decay, operating on a fixed schedule regardless of what anyone on the ground would prefer. And as the power drops, instruments have to be turned off permanently, one by one, to keep the remaining systems alive. The Plasma Wave Science Instrument, the Cosmic Ray Subsystem, each shutdown is a permanent closure. When an instrument goes offline on Voyager, it does not go into standby mode, waiting to be reactivated. The power it was consuming is redistributed to the systems that remain. Turning it back on would require power that no longer exists in the budget. Every instrument shutdown is, in the most literal sense, the end of that measurement capability at the only location in interstellar space where any human instrument has ever operated. We are not turning off a sensor in a lab that we can switch back on tomorrow. We are permanently ending a scientific observation that took 49 years to position itself to make. By 2025 and 2026, the surviving instruments on both spacecraft are down to a small core selected by teams of scientists who had to make painful prioritization decisions about which measurements were most valuable, knowing that the others would be lost forever. By approximately 2030, the power projections suggest there will not be enough electrical output remaining to operate any science instrument at all. The spacecraft will still be functioning in a basic engineering sense, the radio will still be running, the attitude control system will still be keeping the antenna pointed at Earth, but there will be nothing left to measure anything with. By approximately 2036, even that minimal operation becomes unsustainable. The power will be insufficient to maintain the transmitter at a level that allows communication, and after that, silence. Not destruction, not a crash or an explosion or a dramatic final moment, just silence. The transmitter will go quiet. The signal that has been arriving at Earth for nearly 60 years, carrying data across 23 billion kilometers at the power of a falling snowflake, will stop, and Voyager 1 and Voyager 2 will continue moving still intact, still carrying the golden record and the cameras and the 23-watt transmitter, but unable to speak. Ghosts of a mission drifting through interstellar space in permanent silence. Think carefully about the timing of that silence in relation to everything we have covered in this video. The wall of fire, the 50,000 Kelvin plasma shell at the heliopause, was discovered in June of 2025, not from new measurements. From archival data that had been sitting in our databases for years, waiting for the right analytical tools and the right theoretical framework to reveal what was in it. The science from Voyager is not finished. In some important ways, it is accelerating as computational power increases and new models of boundary physics develop. Researchers are finding new things in old data at a rate that is, if anything, increasing. The spacecraft transmitted data for decades that we are still learning to read correctly. And yet, precisely as that process of discovery is intensifying, the instruments that could generate new measurements are going offline. Precisely as our theoretical understanding of the heliopause is sophisticated enough to know what new measurements would be most valuable, what questions we would most want answered, what gaps in the data would most illuminate the physics, the only sensors we have ever placed at the boundary are going dark. The timing is, depending on your disposition, either poignant or simply ironic. We got smart enough to know what to ask right around the time our only source of answers started shutting down. There's something else worth naming here, which is the question of what comes next. The planetary alignment that made the Voyager Grand Tour possible, the configuration of Jupiter, Saturn, Uranus, and Neptune that allowed gravity assists to carry the spacecraft to the outer solar system in a reasonable time frame, recurs once every 176 years. The next window opens in the 2150s. Any mission designed to reach the heliopause by a more direct route, without the benefit of Grand Tour gravity assists, would require either a much more powerful launch vehicle than anything currently flying, or a journey time measured in decades longer than Voyager's. There is no approved, funded mission currently on the books to send another spacecraft to the heliopause. When Voyager goes silent, the interstellar medium loses its only observers, and it may be silent for a very long time. We are watching the end of an era in real time. The only direct measurements humanity has ever taken of interstellar space are being made right now, this year, by these two spacecraft. Every day they remain operational is a day of data we would not otherwise have. Every instrument shut down is a permanent reduction in our ability to understand the boundary we live inside. And yet the spacecraft don't stop. The signal stops, the science stops, the mission stops. The spacecraft just keep going into the dark at 17 kilometers per second, carrying everything we sent with them. That distinction between the end of the mission and the continuation of the journey is the thing this story keeps returning to. Because it turns out the journey, in the end, is the part that doesn't have a stopping point. Part 14. It does not stop. Here is something that takes a moment to fully land. When Voyager 1's transmitter falls silent sometime around 2036, the spacecraft will be moving at approximately 17 kilometers per second, relative to the Sun, outward, into the galaxy, not slowing down, not drifting into a lower orbit, not being gradually pulled back by anything, just moving at 17 kilometers per second in a straight line into interstellar space forever. That speed doesn't diminish. This is the part that the human brain genuinely struggles with, because everything in our everyday experience that moves eventually slows down. Cars decelerate, thrown objects arc and fall. Even satellites in orbit are technically losing altitude millimeter by millimeter due to the thin upper atmosphere's drag. We are wired by lived experience to expect that things slow down. Voyager won't. There is no air in interstellar space. There is no meaningful friction. The gravitational pull of the Sun weakens with distance according to an inverse square law at Voyager 1's current distance. The Sun's gravitational influence is so weak that it would take hundreds of thousands of years to measurably alter the spacecraft's trajectory. For all practical purposes, Voyager 1 is in free fall through empty space on a path that nothing will significantly deflect for longer than human civilization has existed. 17 kilometers per second, long after every person alive today is gone, long after the nations that funded the mission have dissolved and reformed into configurations we cannot predict, long after the buildings at the Jet Propulsion Laboratory in Pasadena have been torn down and replaced with whatever comes after them. The spacecraft will be moving at 17 kilometers per second when the pyramids of Giza have weathered to unrecognizable mounds of limestone rubble, a process that will take tens of thousands of years given current erosion. Rates. It will be moving at 17 kilometers per second when the English language has drifted so far from its current form that a speaker of 21st century English would find it as incomprehensible as a Bronze Age dialect. It doesn't stop. That is not a poetic exaggeration. It is a straightforward consequence of Newton's first law applied to an object in a near frictionless environment. It just keeps going. In the year 2026, which is to say right now, or within the window of when you're likely watching this, Voyager 1 reaches a milestone that is largely symbolic but genuinely worth pausing on. It crosses a distance of 1 light day from the Sun. 1 full day of light travel. To cover 1 light day, light moving at 300,000 kilometers per second, the fastest speed permitted by the laws of physics as we understand them, travels continuously for 24 hours. That distance is approximately 26 billion kilometers. Voyager 1 covered it in 49 years of motion at 17 kilometers per second. A spacecraft built with technology from the mid-1970s, powered by a nuclear battery producing less electricity than a household circuit breaker, guided by trajectory calculations made on computers that would be considered primitive museum pieces today, crossed 1 light day of distance from its home star in less than half a century. There is something in that fact that resists easy categorization. It's not quite triumphant and not quite humbling. It's both at once. Now let time move faster. Go forward 300 years from today. Voyager 1, still moving at 17 kilometers per second, still silent, still intact, reaches the inner boundary of the Oort cloud. The Oort cloud is one of those concepts that sounds simple until you actually try to picture it, at which point it becomes difficult to hold in the mind all at once. It is an enormous, roughly spherical shell of icy bodies comet nuclei, frozen remnants of the early solar system surrounding the Sun at distances ranging from approximately 2,000 astronomical units at its inner edge to perhaps 100,000 astronomical units at its outer boundary. That outer boundary is about 1.5 light-years from the Sun. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. The Oort cloud extends more than a third of the way to the nearest star. Within the Oort cloud, the individual objects are not clustered. They are not like the asteroid belt, which, despite its reputation as a crowded region, is actually navigable without much difficulty. The Oort cloud contains perhaps several trillion comet nuclei distributed across a volume of space so enormous that the average distance between any two objects is measured in tens of millions of kilometers. You could travel through the Oort cloud for your entire life and never come close enough to a single object to see it with the naked eye. It is a shell made of almost nothing, surrounding a solar system made of slightly more than almost nothing, in a galaxy made mostly of the space between things. And Voyager will enter it 3 centuries from now and spend the better part of 30,000 years crossing it in complete silence, carrying the golden record. During those 30,000 years, the sun itself will not be standing still. The sun moves through the galaxy at approximately 26 kilometers per second, tracing a slow orbit around the galactic center that takes about 225 million years to complete. On much shorter timescales, the sun is also moving through local structures in the interstellar medium clouds of gas and dust that vary in density, temperature, and magnetic field organization. And here is something that tends to get left out of the standard Voyager story. In approximately 1,900 years, the sun will exit the local interstellar cloud. The local interstellar cloud is the specific region of interstellar gas our solar system currently occupies. It's a warm, relatively low-density wisp of partially ionized hydrogen and helium, about 30 light-years across, moving through the galaxy as a coherent structure. The heliosphere, the shape Voyager measured, the boundary it crossed at 121 astronomical units, the deflated croissant with the wall of fire and the magnetic highway, is shaped by the interaction between the solar wind and this specific cloud. The pressure of the local interstellar cloud against the heliosphere is one of the factors determining where the heliopause sits and what form it takes. In 1,900 years, that cloud ends, the sun exits it and enters whatever comes next, a different region of interstellar space with different density, different temperature, different magnetic field organization. And when that transition happens, the heliosphere will change. Its size, its shape, its boundary location, all of it will shift to reflect the new balance of pressure between the solar wind and the new surrounding medium. The heliopause that Voyager measured at 121 astronomical units may no longer be where the boundary is. The deflated croissant may inflate or compress or change its proportions. The wall of fire may strengthen or weaken depending on the new magnetic geometry. The boundary Voyager crossed will no longer exist in the form we measured it. This is the part of the heliosphere story that almost never gets told, and it's one of the most important parts. The heliosphere is not a permanent feature of our solar system. It's a dynamic structure that has been changing throughout Earth's history and will continue changing for the rest of the sun's life. The sun has been moving through different regions of the interstellar medium for 4.5 billion years, and the heliosphere has responded to each transition. Sometimes the surrounding medium is thin and low pressure, and the heliosphere expands, the heliopause pushes outward, possibly to distances significantly greater than the 121 astronomical units Voyager measured. Sometimes the surrounding medium is dense, a molecular cloud, or the compressed shell of gas around a supernova remnant, and the heliosphere contracts dramatically, the heliopause pushed inward to perhaps a few tens of astronomical units, leaving the outer planets exposed to the full flux of galactic cosmic rays with only the heliosphere's reduced shielding. There is geological evidence that these compression events have happened. Certain isotopes produced by cosmic ray bombardment, beryllium-10, chlorine-36, are preserved in ice cores and sedimentary rock in ways that record changes in cosmic ray flux reaching Earth's surface over millions of years. Some of those records show elevated cosmic ray exposure at particular periods that align, at least roughly, with known events in the sun's journey through the galaxy. Some researchers have connected these periods of elevated cosmic ray flux to episodes of increased glaciation, the idea being that cosmic rays can influence cloud formation and atmospheric chemistry in ways that affect climate. The evidence chain is long, and each link carries uncertainty, but the basic connection between the heliosphere's size the cosmic ray flux reaching Earth, and conditions at Earth's surface is physically plausible and increasingly well supported in outline, even if the details remain contested. What this means for the deepest question in this video, what the boundary looks like when no one alive today is around to see it, is that the answer changes depending on when you ask it. In 1,900 years, the boundary reforms in a new medium. In 30,000 years, Voyager is still crossing the Oort cloud in silence, while the heliosphere continues its own slow evolution. In 1,000,000 years, the Sun has moved far enough through the galaxy that its local interstellar environment is unrecognizable compared to today. The boundary exists in all of these futures, but it is not the same boundary. It was never the same boundary. The heliosphere breathes on timescales we can barely imagine, and what Voyager measured is one breath, one configuration, at one moment in the 4.5 billion year history of a living, changing structure surrounding a moving star. The boundary Voyager found will change. It already is changing, and Voyager, silent and intact and moving at 17 kilometers per second, will drift through whatever the boundary becomes, and then past it, and then through the Oort cloud, and out the other side, heading towards stars it will never reach, carrying a record of a civilization that once lived inside a boundary it barely understood, at the moment it first touched it. Part 15. The First Encounter, 40,000 years. In approximately 40,000 years, Voyager 1 will make its closest approach to another star. Take a moment with that sentence before we move on, because it contains a scale of time that the human mind isn't really built to process intuitively. 40,000 years ago, anatomically modern humans were painting animals on cave walls in what is now France and Spain. Agriculture hadn't been invented. Writing hadn't been invented. The wheel hadn't been invented. Every single thing we call civilization cities, mathematics, philosophy, science, spacecraft, all of it fits inside the last 40,000 years with room to spare. And Voyager 1, moving at 17 kilometers per second from the moment of its launch, will spend that entire span of time, all of recorded history and all of prehistory, back to the cave paintings, just getting close to its first star, not reaching it, not orbiting it, just getting close to it. The star is called Gliese 445. It's a red dwarf, the most common type of star in the galaxy, small and dim and cool by stellar standards, burning hydrogen slowly enough that it will remain on the main sequence for hundreds of billions of years, long after our Sun has died. Gliese 445 is currently located in the constellation Camelopardalis, approximately 17.5 light-years from Earth. That distance will change over time, because stars move. Everything in the galaxy is in motion, drifting relative to everything else on trajectories shaped by the gravitational field of the Milky Way as a whole, and the local pulls of neighboring stars and gas clouds. By the time Voyager 1 reaches the vicinity of Gliese 445, 40,000 years of stellar drift will have brought the two objects, the spacecraft and the star, to within approximately 1.6 light-years of each other. 1.6 light-years. That sounds close, stated plainly. It is not close. 1 light-year is approximately 9.5 trillion kilometers. 1.6 light-years is about 15 trillion kilometers. For comparison, the distance from the Sun to its nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years. Voyager 1's closest approach to Gliese 445 will be at a distance roughly equivalent to 200 times the Sun to Proxima Centauri gap. There will be no gravitational interaction, no tidal effect, no detectable influence of any kind passing between the star and the spacecraft. Voyager will simply move through that region of the galaxy, at 1.6 light-years from a red dwarf it will never see up close, and continue in the same direction at the same speed, unchanged by the encounter in any measurable way. Voyager 2, travelling on a completely different trajectory, diverging from Voyager 1's path by the specific angles, determined by its own planetary encounters, and gravity assists back in the late 1970s will have its own stellar approach around the same period. In approximately 40,000 years, Voyager 2 will pass within about 1.7 light-years of a star called Ross 248, another red dwarf, another dim, cool, long-lived star that will outlast our Sun by an enormous margin. Ross 248 is currently about 10.5 light-years from Earth, also moving through the galaxy on its own trajectory, and the geometry of Voyager 2's path and Ross 248's motion will bring them to within 1.7 light-years of each other, around the same 40,000-year mark. Think about what it means that both spacecraft launched within 16 days of each other from the same launch site in Florida in the same year by the same agency will make their first stellar approaches within roughly the same time frame to two different stars in two different directions at nearly the same minimum distance. That's not a planned outcome. Nobody in 1977 sat down and designed the mission so that both Voyagers would have their first near-stellar encounters simultaneously 40,000 years later. It's a consequence of the geometry of launch windows and planetary alignments and gravity assist trajectories playing out over cosmological timescales. Two bottles thrown into the ocean at the same moment, drifting on completely different currents, washing up on two different shores at approximately the same time. Except the ocean is interstellar space, and the shores are 40,000 years away. And neither approach involves anything we would recognize as an event. This is the part that really forces a confrontation with the scale of interstellar distances. In human terms, in narrative terms, a spacecraft approaching a star should be dramatic. It should be a moment, a crossing, an encounter, a discovery. But at 1.6 light-years of minimum distance, there is no moment. There is no crossing. There is just Voyager, still moving at 17 kilometers per second, passing through a region of space that happens to be marginally less empty than the regions around it, because there is a red dwarf star somewhat less than 2 light-years away. And then that region is behind it, and the next region is ahead of it, and the speed is still 17 kilometers per second, and nothing has changed. This is the real lesson of interstellar scale, and it's one that's worth sitting with rather than quickly moving past. 17 kilometers per second is not a slow speed by any human standard of reference. At 17 kilometers per second, you could travel from New York to Los Angeles in under 4 minutes. You could circle the Earth at the equator in just over 37 minutes. You could travel from the Earth to the Moon in about 6.5 hours. At 17 kilometers per second, you are moving at a pace that would make any vehicle in human history look stationary by comparison. And it will take 40,000 years to get within 2 light-years of the nearest star in Voyager's path. The nearest star to our Sun, not the nearest star in Voyager 1's specific trajectory, but the nearest star to us in any direction is Proxima Centauri, at 4.2 light-years. At Voyager's speed, reaching Proxima Centauri would take approximately 73,000 years, not 40,000, 73,000. If you launched Voyager 1 toward Proxima Centauri at the moment of Homo sapiens' first appearance on Earth, roughly 300,000 years ago, it would still be more than 200,000 years from arriving. Interstellar distances are not merely large. They are of a completely different categorical magnitude than anything in human experience. Our intuitions about space, built from a lifetime of moving around on a planet and occasionally looking at photographs from spacecraft, do not prepare us for what the numbers actually mean. And yet interstellar space is not simply empty. This is something Voyager's crossing of the heliopause has already begun to teach us, and it's worth extending into the broader interstellar environment that both spacecraft are now entering. The local interstellar medium, the region of gas and magnetic fields surrounding our solar system for tens or hundreds of light-years, has structure. It has the local interstellar cloud that the Sun is currently moving through. It has the local bubble, a region of hot, thin gas approximately 300 light-years across, carved out over millions of years by a series of ancient supernovae whose remnants have long since dispersed. It has density variations, filaments, magnetic field organization, shaped by the cumulative history of stellar births and deaths in our galactic neighborhood over billions of years. As Voyager moves through this medium over the coming thousands and millions of years, it will pass through regions of different density, different temperature, different magnetic structure. Some of these regions will be slightly denser remnant shells of old supernova shockwaves, compressed gas at the boundaries between different interstellar cloud systems. Some will be thinner, the evacuated interiors of old bubbles blown by stellar winds. The spacecraft will pass through all of it at 17 kilometers per second, registering none of it, because its instruments will have been silent for tens of thousands of years by the time any of this becomes relevant. But here's the connection that matters for the central story of what Voyager found at the heliopause. The same physical processes that created the complexity at the boundary, the asymmetry, the magnetic structure, the variable density, the dynamic interface between different pressure regimes are the processes that created the structure of the interstellar medium that Voyager is now traveling through. The deflated croissant shape of the heliosphere is a response to the specific pressure and magnetic field of the local interstellar cloud. The wall of fire at the heliopause is driven by the specific angle between the solar magnetic field and the local galactic field. The magnetic highway is a consequence of the particular alignment between those two field systems in the direction Voyager 1 was traveling. All of these features are local. All of them are specific to this moment in the Sun's journey through this particular region of the galaxy. And as Voyager moves farther from the heliopause and deeper into the interstellar medium, it is moving into the same kind of structured, variable, magnetically organized environment that created the boundary it crossed just on scales that dwarf the heliosphere entirely. We sent 2 spacecraft into that environment in 1977. They crossed its first boundary and told us the boundary was nothing like we thought. Now they are inside it, moving through it in silence, heading towards stellar approaches that are 40,000 years away and will involve no drama whatsoever. And beyond those approaches, more silence, more movement, more interstellar medium, structured and varying and magnetic, that no instrument of ours will ever sample at close range. The distances are the point, not as a source of despair, but as the actual, unvarnished fact of what interstellar space is. Voyager crossed the heliopause and entered this space. That crossing took 47 years. The next meaningful landmark is 40,000 years away. And after that, millions. And after that, billions. The spacecraft doesn't know any of this. It just moves. 17 kilometers per second into whatever comes next. Part 16. The long end, billions of years. In about 5 to 6 billion years, the Sun will run out of hydrogen fuel in its core. This is not a controversial prediction. It is one of the most well-established conclusions in all of astrophysics, derived from our understanding of nuclear fusion, stellar structure, and the observed properties of stars at different stages of their lives. We have watched other stars go through this process. We understand the physics well enough to model it in considerable detail. And what the models tell us, with high confidence, is that the Sun's main sequence life, the long, stable period of hydrogen burning that has made life on Earth possible for 4.5 billion years, will end. The core will contract. The outer layers will expand. The Sun will swell into a red giant, growing to perhaps 100 times its current diameter, its outer atmosphere extending to somewhere in the vicinity of Earth's current orbit, possibly beyond it. What happens to Earth specifically during this process is a question the models answer with slightly less certainty, because the details depend on things like how quickly the Sun loses mass during its giant phase and how that mass loss affects Earth's orbital radius. If the Sun loses mass gradually enough, Earth's orbit may migrate outward as the Sun's gravitational hold weakens, potentially staying just ahead of the expanding stellar atmosphere. If the expansion is faster relative to the mass loss, Earth may be engulfed, swallowed by the outer layers of a star it has orbited for 10 billion years. Either way, the surface of Earth will be sterilized long before the red giant phase reaches its peak. The Sun's luminosity will increase steadily over the next billion years, even while it remains on the main sequence, and within that time frame, far shorter than the 5 billion years to the red giant phase, the oceans will likely evaporate, and the conditions for surface life as we know it will end. 5 billion years is when the star itself transforms. The habitability problem arrives considerably earlier. During the red giant expansion, the heliosphere will change dramatically. As the Sun brightens and its outer layers expand, the solar wind will intensify, more material flowing outward at higher rates, driven by the increased radiation pressure of a more luminous star. The heliosphere will expand with it. The heliopause, the boundary Voyager, measured at 121 astronomical units. The line that turned out to be 20 astronomical units farther than predicted will push outward to new distances, driven by a solar wind more powerful than anything the Sun produces today. Then, as the red giant phase progresses and the Sun begins losing mass at rates far exceeding its current solar wind output, the character of that wind will change again. The composition will shift, the pressure will fluctuate. The heliosphere will respond to each change, expanding and contracting and reshaping itself in ways that our current models of heliospheric physics are only beginning to be able to address. A different Sun will drive a different heliosphere, one that may look nothing like the deflated croissant Voyager revealed, shaped instead by the chaotic, mass-losing dynamics of a dying star. None of this will affect Voyager. By the time any of it happens, both spacecraft will be so far from the Sun that the red giant phase is, from their perspective, simply a distant stellar event happening far behind them. We are talking about 5 billion years of continued travel at 17 kilometers per second. In 5 billion years, Voyager 1 will have covered a distance so enormous that expressing it in astronomical units becomes cumbersome. We would need to talk in terms of thousands of light years. The thermal output of a red giant, the shockwave of a planetary nebula, the slow dimming of a white dwarf, none of these events will reach the spacecraft in any meaningful way across those distances and timescales. Voyager will simply be somewhere else, somewhere very far away and very empty, still moving at 17 kilometers per second, still intact, still carrying the golden record. The golden record deserves more time than it usually gets in the Voyager story, because it is in some ways the most philosophically loaded object humanity has ever created. Each Voyager spacecraft carries a 12-inch disc made of copper and plated with gold, encoded with a collection of sounds and images chosen to represent life on Earth to any intelligence that might someday find it. 115 images, selected from across human culture and natural history. Greetings spoken in 55 languages, ranging from Akkadian to Wu Chinese. Music from 27 cultures, Bach and Beethoven and Chuck Berry. Azerbaijani bagpipes, Peruvian wedding songs, Navajo night chants, a pygmy girl's initiation song. Natural sounds, ocean surf and wind and rain. The crack of thunder, the songs of birds, the calls of whales, the sound of a chimpanzee, a human heartbeat, a mother's first words to a newborn child. On the cover of the record, instructions for playing it are engraved using diagrams based on the hyperfine transition of hydrogen, a quantum mechanical property of the most common element in the universe, chosen as a reference point that any civilization advanced enough to encounter the record would almost certainly understand. The instructions explain how to construct a device to play the record, how to decode the images, how to interpret the sounds. They are addressed to no specific recipient. They are addressed to whoever finds this. The record is expected to remain physically intact for approximately 1 billion years. Gold plating on copper in the near vacuum of interstellar space with negligible corrosion and very low radiation flux from any nearby source, the material science is favorable. 1 billion years. Consider what that number means when placed against the history of life on Earth. Complex animal life creatures with hard parts, with eyes, with nervous systems, capable of something approaching awareness, has existed on Earth for roughly 540 million years, since the Cambrian explosion. The golden record will survive approximately twice that span. Dinosaurs existed for about 165 million years before the asteroid impact that ended the non-avian lineages 66 million years ago. The golden record will survive more than 6 times the entire dinosaur era. Modern humans, Homo sapiens, in our current anatomical form, have existed for perhaps 300,000 years. The golden record will survive more than 3,000 times as long as our species has existed so far. It will still be physically intact, drifting through the galaxy, long after the sun has become a white dwarf and the inner solar system has cooled to a frozen, airless ruin orbiting a dying star. Carl Sagan, who championed the golden record and played a central role in designing its contents, said something about it that has stayed with me since I first encountered it. He said the record was not really intended for aliens, not primarily. The probability that it will ever be found by any intelligence is so small as to be effectively negligible. The galaxy is too large, the timescales too long. The likelihood of any civilization being in the right place at the right time to intercept a specific object moving at 17 kilometers per second through interstellar space is vanishingly small. He said the record was intended for us. It's a portrait, a statement of what we were, made at a particular moment in our history, sent outward as an act of declaration rather than communication, a message in a bottle thrown not into an ocean but into the universe, with full awareness that it will almost certainly never be read. We sent it anyway, not because of the probability, because of what the act of sending it said about us. That distinction matters more the longer you sit with it. The golden record is not optimistic in the naive sense. It doesn't assume we'll be found, doesn't count on discovery, doesn't depend on a response. It's optimistic in a harder sense. It assumes that the act of reaching outward has value independent of its outcome. That making a record of what we valued, even if no one ever hears it, is worth doing. That sending something beautiful into the void is better than not sending it, even when the odds of it mattering are essentially zero. That is not naive. That is something closer to the most honest and clear-eyed form of hope that doesn't require a guaranteed result to be worth acting on. And that gesture, the golden record on a spacecraft that has now left the solar system and will never return, is also, I think, the most compressed version of what Voyager represents as a whole. We built machines that weren't supposed to survive. They survived. We designed them for a 5-year mission. They ran for 49 years and counting. We aimed them at planets. They found the edge of everything we knew, and then crossed it, and then found that everything on the other side was different from what the models said. We thought the boundary was in one place. It was in another. We thought it was a certain shape. It was a different shape. We thought crossing it would produce a clear magnetic signature. It barely moved. We thought the boundary was passive. It was burning. Every anomaly was a correction. Every correction pointed the same way. The universe is not obligated to match our models of it. Our solar system's front door, the structure we had been modeling for decades, the boundary we thought we understood, turned out to be stranger and more complex and more alive than 4 decades of careful theoretical physics had led us to expect. And the only reason we know this is because 2 machines built with 1970s technology kept working long past every reasonable expectation, drifting outward at 4 watts per year of power loss, carrying 68 kilobytes of memory and a transmitter weaker than a kitchen light, until they finally reached the door and walked through it and told us we'd had the address wrong the whole time. The boundary moved, the shape was wrong, the crossing was a highway, not a wall, the edge was burning, the storms were leaking into the galaxy, the magnetic fields aligned in ways that broke the measurements. 7 anomalies, 7 corrections. And the answer they all point toward is the same one. We had barely started to understand our own neighborhood before Voyager showed us how little we knew. The signal will stop, the science will stop, the engineers will retire and eventually be gone, but the spacecraft will keep moving, 17 kilometers per second, through whatever the galaxy becomes around them. Through the death of our sun and the cooling of our solar system, and the slow transformation of everything we've ever known into something unrecognizable, they don't stop, they just keep going. Carrying a record of a species that once lived inside a boundary it thought it understood, and that had the extraordinary luck and the extraordinary stubbornness to build 2 machines that lived long enough to show them they were wrong. The boundary isn't the end of the story. It never was. It's just the last page we managed to read.